Good morning, everyone. Next up, we have Davey Shafik, who's going to be talking to us today about HTTP2 and asynchronous APIs. Let's make him feel welcome.
Good morning. I'm going to be speaking about HTTP2 and asynchronous APIs. My name is, this is not working because I didn't plug it in. There we go. Okay. My name is Davey Shafik. I am a developer. I'm an author. I'm an open source contributor. I'm the release manager for PHP 7.1, which is kind of cool. And I'm at dshafik on Twitter. So if you have any comments or questions after the fact, please reach out to me there. I work for Akamai. We do cool stuff. But most importantly, today is my birthday. So I'm sure all of you were aware, but that is my Amazon wish list. They do same-day delivery here in Portland. I'm just saying. And tonight, I'm going to celebrate with some Pi karaoke at the Alibi at 8 p.m. So if you want to join me, please come by, and hopefully we'll have some fun. More seriously, I work with this group, Prompt. I always mention them. It's a group to get people talking about mental health issues in technology. So check out mhprompt.org. This is really, really important. On to HTTP2, or H2. So HTTP2 has been around for about a year in official spec form. We know that it's a real thing because it has a logo. But what is it? So HTTP2 is actually two separate specifications. It is RFC 7540, which is the HTTP2 spec, and 7541, they are consecutive, which is HPAC, which is header compression, which we'll talk about today. It was created by the IETF working group, which is chaired by Akamai's Mark Nottingham. So HTTP has been around for a while. 0.9 came out in 1991, followed 5 years later by HTTP 1. 3 more years later, they said, we did everything wrong, let's tweak it, and we got HTTP 1.1. And this is the current state of the web. In 2009, the Google folks, Chrome, said, that's not good enough, we're going to create something better, and they created Speedy. And then just last year, 2015, based on Speedy, the IETF working group created HTTP 2. So most importantly, let's talk about browser support. Currently, 60% of browsers on users' machines support HTTP 2, which is pretty awesome. That includes Chrome and Chrome Mobile, Firefox, IE 11 if you're on Windows 10. It includes Microsoft Edge, Safari on El Capitan on iOS 9, and Opera, but nobody uses it, so nobody cares. I gave that joke in Norway. It didn't go down so well. It's binary instead of text. This is the change that everyone kind of knows about. This is quite significant. It means that it's harder for us to, say, issue requests via Telnet, but it's way more efficient. It's more efficient on the wire in terms of message size, and it's also more efficient and more consistent for parsing, so that we use less resources both on the client and the server side. It is fully multiplexed instead of ordered and blocking, which means that you can use one connection for parallel requests. And this is kind of the key of HTTP2. If you take away nothing else, the idea and the concept behind this is what this is all about. It uses header compression, which is that HPAC stuff, which further reduces overhead, and this is really cool as well. But my favorite feature is called server push. And what server push allows you to do as a server is to proactively push assets down to a client that is making a request, such as if they request an HTML page, you can say, well, you're obviously going to need the CSS and the JavaScript and the font. So rather than you making requests for those, we're actually going to send those proactively to you in addition to the HTML page. And then that goes into the browser's cache. And when they try to make that request, it'll come out of the cache directly, which is obviously a performance increase. So what does HTTP2 mean for you as an application developer? To be quite honest, it's transparent. It's mostly going to be handled by your web layer. So Nginx, Apache, whatever you have sitting in front of your application is going to be handling the fact that the client is using HTTP2. So what's the point? Like, if we can just turn it on and forget about it and our applications don't need to change, why do we care? The fact is that HTTP 1 sucks. Now, I have to be very clear here. the semantics and ideas and methods and everything in HTTP1 are all directly translated to HTTP2. But to get around some of the shortfallings of HTTP1, we've come up with a bunch of tools that help us make it more performant. So things like minifying and concatenating JavaScript and CSS. Inlining small bits of JavaScript and CSS is known as the critical path. Using image sprites, data URIs, and domain sharding. All of these are techniques that we've come up with to improve the performance of HTTP1. And the fact of the matter is that all of these things are hacks. They're very clever hacks. Certainly, I couldn't come up with them on my own, but they're all hacks. So if you remember this concept of being able to use one connection for parallel requests, this becomes really important in removing the need for all of those hacks. So let's take a look at an example. Think of an HTML page with a form with multiple file inputs, and we're going to upload multiple images. Traditionally, we would do sort of a serial upload. So the browser would submit, would open up a TCP connection, and it would submit all of those images as one blob of data in the HTML form data. We go to our server, and on the back end, we may then want to put it on disk or say on S3 or Akamai Net Storage, and we would send multiple requests then for each of those images to the back-end storage. This is not ideal. So we start doing things concurrently, right? So now we create 3 connections. We send 3 images simultaneously. On the back end, we do the same thing. We create 3 connections, and we send 3 images simultaneously as they come through. So that's the first use case. The second one we're going to look at is APIs. So obviously, from the name of the talk, this is what you're hopefully expecting. So really simple API. Please don't judge me. It's meant to fit on slides. Fetching a blog post with comments. Like, this seems like a pretty common use case. So we have a client and a server. We open up a TCP connection. We do a GET request. We get a JSON response. And maybe that looks something like this, right? So JSON object, type post, ID 1, et cetera. Most importantly, we have 2 links at the bottom. The first one goes to the author information, and the second one goes to the comment information. So let's go ahead and try and get the comments. Now, follow that URI, get another JSON response. At this point, you have to make a choice. Do you respond with all of the comments, or do you respond with a collection that links to all of the individual comments, because they are specific individual resources? So ideally, in a wonderful world, we would respond with this collection. So here's a list of comments, just a simple array. So we're going to go ahead and fetch all of those, right? TCP connection, blah, 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 right? We get this. And here's a comment, which has a link to author information, for example. So minimum, we're making 6 requests, possibly connections, more likely 14 requests. It's not very good. So let's take a look at multiplexing. Let's look at this idea of one connection concurrent requests. Here we create one pipe, and we send all of our requests at once, and we get all of our responses as they come through, right? This is obviously an improvement, like less overhead, potentially quicker, all these kind of things. What does it look like in code, right? So we're going to start with this little bit of code, num request 378. It's not a random number. If you go to http2.akamai.com, you see this little demo. And this demo is stolen from Gopher Tiles. I don't say stolen. I think it says demo concept inspired by. We'll go with that. So on the left-hand side, we have multiple requests loading these 378 tiny little tiles to create the world. And then on the right-hand side, we have it coming in HTTP2. And as you can see, there is a significant difference here. 17 seconds on the left and just over 3 seconds on the right. Right, that's significant. So on the right-hand side, we're doing multiple concurrent requests with multiplexing. So I'm going to use PyCurl. Who uses, say, requests? OK, I like requests, but it's not HTTP2 yet. I don't believe so. Curl is my tool of choice. So very simple. We will do a for loop on that number of requests, create a bunch of curl clients, set some options. So we set the URL. Sorry, my phone is ringing. It's probably my mother calling to wish me a happy birthday. OK, so we set the URL. We set a buffer into which we're going to write the response. And then we go ahead and perform the request. And that takes 20 seconds. OK. Now let's take a look at HTTP 2. So here, the only change that we're going to make is we are going to set the HTTP version to HTTP 2. It's a very simple change. And when we do that, through the magic of more performant HTTP 2, it now takes 34 seconds. Obviously not the result we want, and we'll look into why that is in a little bit. Now let's look at concurrent. So for this, we're going to use curl multi. And what curl multi does is it's a multiple handler. You will add the individual clients to it, and then it will manage all of the requests. So we instantiate curl multi. We set pipelining to 1, which is HTTP 1 pipelining. And then we append our clients that we created earlier, and then add them to the multi. And then this little bit of code is actually, I hate this piece of code, and it looks exactly the same in every single language that I've done, which is PHP, Ruby, and Python. What essentially this does is it has one while loop that will continue running until we get a response, and then the second while loop will take over, and it will actually handle the responses. So when we do this with HTTP 1, it goes down to 6 seconds. So from 20 to 6. This is good. If we now switch to HTTP 2 multiplexing, we change pipelining to 2. And of course, we set the HTTP version. It's the only change we make. This is identical, and I still hate it. And now it takes 4 seconds. So this saves us another 2 seconds over changing to concurrent HTTP 1. So this is good. All right, so why was the original example slower? So in an effort to make HTTP 2 backwards compatible, we have this wonderful HTTP 2 negotiation that happens. And this happens in one of 2 ways. It will either be over TLS, it will be part of ALPN, or it will be in plain text, and you'll send a request with a request upgrade, and you will actually get an HTTP 101 switching protocols back. And from that point on, you'll be HTTP 2. So HTTP 2 is completely backwards compatible, if you want it to be, which is fantastic. We turn it on. If our clients are HTTP 2, they work. If they're not, then they continue using HTTP 1. Some really interesting things that we can do with our applications around this idea. There are 2 protocol identifiers, H2, which is HTTP 2 over TLS, and then H2C, which is HTTP 2 over TCP in plain text, which, as I said, uses that HTTP 1 request. So ALPN, Application Layer Protocol Negotiation, is part of the TLS handshake. It was published as an RFC 7301 in 2014, so it's been out there a while now. You may have read a blog post in the last week or 2 that said Chrome broke HTTP 2 for most everybody, because most Linux distros, for example, are running an older version of OpenSSL that doesn't support ALPN yet. So Chrome doesn't have it, and therefore HTTP 2 doesn't work. So you need to be running a new version of OpenSSL to get ALPN. Very important. Now, because it is binary, I'm going to show you the H2C plain text upgrade so you get an idea of what this looks like. So we do a simple GET request. We say upgrade H2C, send HTTP 2 settings, which is actually part of the HTTP 2 protocol. And then as you see as a response, if we do support HTTP 2, then we'll send a 101 switching protocols. If you don't support it, you just send the response to the GET request, right? Now, this can be a different type of request. It doesn't have to be a GET. It could be an options or a head. It could even be a put, post, or delete. Why? I'm not sure why you do that. It's important to understand if you send a message body, then until that message body is received, the upgrade cannot happen. That becomes very important when being in parallel with multiple requests is important. It must also include this HTTP 2 settings header, which basically says the settings about the request. All browsers require TLS for HTTP 2 currently. I am not aware of there being an exception for localhost. I do want to check on that. Seems like a good idea. They did that with the location APIs recently. But yeah, must have TLS. So go check out Let's Encrypt if you haven't seen it yet. Free TLS certificates. You can also do direct connections with HTTP 2. So this is known as prior knowledge. So this is a performance benefit. So where we were doing that for loop with many requests before, and it got slower, the reason is that we're actually creating new connections with every single iteration of the loop. We're not actually using one connection. And we have the upgrade with every single one of them. Now, with prior knowledge, it's possible if both sides know they have prior knowledge of support for HTTP2, they can do a very simple, they send a token essentially to upgrade. You know, do you speak HTTP2? No, I'm broken. Yes, let's just go on, right? So yeah, that's something that's possible. If you're writing your own clients and servers, you should be looking into that. Server push. As I mentioned, this is my favorite part of HTTP2. This is where the excitement is for me. So if you remember, we had this concept of multiplexing. The issue here is that we're still making sub-requests, right? Now, we have a concept of we want to make our APIs performant. So what we'll do is we'll munge many sub-documents into one larger document, right? Rather than send multiple requests, we'll just send all the information that we think you're going to need. Might look something like this instead. I'll zoom in a little bit. So here we have the author information just right there in the post. Comments is now an array of objects with all of that information. You notice that we have the author information embedded, which as the author of the post, that's now duplicated. That's terrible. Here we have someone that replied to a comment twice, so their author information is duplicated as well. Like, this is inefficient, but is better in terms of transfer across the wire, potentially, or requests across the wire. So let's look at something a little different. Server client, TCP connection, get post 1, same as before, application JSON response. Now, as a server, we can say, well, most people who want the blog post also want the comments, so we're just going to send you that. Sends that array. We're also going to send you those individual comments, right, because we know you're going to want those. We'll send you the author information, their avatars, et cetera, right? So we can proactively decide that we're going to send this information to the client. Now, what's really cool on the client side is you actually have the option to reject those requests. So you can look at the URL that's being sent to you. You can look at the headers. You can say, I don't actually need that information now, so I'm just going to not accept it. And that data doesn't go over the wire at all. So rather than munging together a bunch of data that may potentially be needed, the client now is in control of what data it's going to accept and request. And you can actually dynamically change that. So for example, if you are on mobile, you may reject any image pushes, right? This is really cool. What it also means is CSS and JavaScript minification is completely unnecessary. gzip compression, multiplexing, and server push mean that those things are no longer something that's important to us. We can just send it. For those who are concerned about this, gzip compression alone usually gets within 1% of the size of CSS and JavaScript minification plus compression. Now, HTTP2 stuff is made up of streams. You'll come across this. Each request and response is a stream. They are comprised of what are known as frames. We'll get into that. They have an ID. They have a weight, which is between 1 and 256. And they have potentially a dependency. And those two things are really cool. So with dependencies, we can say that stream B depends on stream A. So until stream A has been received by the client, don't bother sending stream B. Same thing for stream C. It depends on B, so until B is sent, don't send C. With weights, we can specify how much relatively of the resources are used for a given response or request. So stream A has a weight of 1, stream B has a weight of 2, so it gets 2 times the resources, whatever that may be in context. Stream C has a weight of 3, so it has 1.5 times the amount of resources of B and 3 times that of A. And the client and the server will just decide what that's going to be. So frames. Every message is comprised of multiple frames. Those may be things that represent, say, headers, which should come at the beginning of the responses, data or settings. Each frame has a common header. They're easy and efficient to parse, which is kind of the whole point here. And they could be interleaved, which is really cool. That's how we get multiplexing. We can send a frame from stream 1, a frame from stream 2, stream 3, and just keep going around. So that's how we get multiplexing. And it's also how pushes work. There's a push promise frame, and that's how the client knows that that's what it's receiving. So here, for example, we have on the left-hand side a post request. The bunch of headers get sent as a header frame. And then we have a JSON body, which would be sent as a data frame. Like, this is pretty simple. We also have, on the topic of headers, HPAC. Now, HPAC came about because in Speedy, there was actually a security vulnerability. Apparently, if you compress something and then encrypt it, that makes it a lot easier to decode because of repeated strings. So instead, we have HPAC. And what HPAC is a known value, a known set of values in an index. And as a server, we can just refer to those index IDs rather than sending the value itself. Now, those can represent a name and a value. And you'll see stuff like statuses and stuff showing up in their parts that aren't normally part of the headers, or just a name. They're either statically encoded or Huffman encoded. And this is the first of 64 entries. So if you see here, like number 2 is the method get. We have statuses starting at number 8, schemes. We have paths in there even that are hard-coded in there. What's really cool about this is that you can actually append to this table custom entries. So for example, if you want to send cookies, session cookies, you can send it once and then just start referring to the ID in that table rather than sending that session cookie over and over again. So you can see we're going to get quite a bit of compression out of this. It's pretty cool. All right, so the last thing I want to touch on is potential for new architectures and techniques, and this is where things get exciting for me. So let's talk about delivering a page, right? So we've already talked about this idea of pushing. So let's see what this looks like. So we open up a TCP connection. We do a GET request, and we get our response. And then we can start to push our critical path information and our logo, for example. And we can set a dependency on, say, our fonts for our CSS. We can send all of our rest of our JavaScript as a dependency on the critical path JavaScript. Maybe we want to send a splash image. And then we can follow up with, say, the main styles, right? This has a lot of potential to change how we build things right now. And I think there's a lot of experimentation stuff that we're all still going through to find out best practices. On the API responses, similar kind of thing. In fact, the same header, because I messed that up. Make a GET request, get our response. We can start to post things. Now, rather than potentially just shove everything back like we were doing before, we can be a little bit smarter about this. So let's respond with the comments plus the author information. We can set a dependency for the following comments, for example, and the author image, and another dependency for the author information of the comments, right? These are things that are possible now. So in summary, no more hacks. All of that tool chain that we built around HTTP1 stuff goes away. Huge performance wins if you do it correctly. 60% market share. HTTP2 is awesome. I am so excited about this, and I hope you are as well. I would love to, if we have a few minutes for questions, or reach out to me at dshafik on Twitter, dshafik@akamai.com. These slides will be available as soon as I click the publish button at daveyshafik.com/slides. Thank you very much.
So we do have quite a few minutes for questions, actual questions. If you can ask a question, then it will be a question. While people are lining up, I had a question.
Yes.
What's the specific limitation to requests right now that this won't work, why you had to use PyCurl?
So request just doesn't have support for HTTP2 yet. I'm not confident in that anymore. It's been a while. So, and I believe the author's here, so I'm not going to. Could you speak up as well?
Yes. You said, aside from those new architecture possibilities at the end, shouldn't have to do much different in server-side code because the Nginx or Apache or whatever will negotiate most of the differences, right?
Yeah, so the way that pushes work right now is the application will actually send a link header with a rel equals preload, and then the server will take over from that point and make a sub request. Nginx does not yet support push, and it's not on their roadmap, and I'm kind of mad about this. So Apache supports it. There's like H2O, which is a proxy you can put in front.
May I follow up?
There is also some question of supporting, as I mentioned, there's a migration path because there's that support for HTTP1. I think what we may see going forward is if you are an H1 client, then we're going to send you minified concatenated type stuff, and if you're not, then we're going to send pushes. So that obviously has an impact on our application layer, but I think it's minimal, and I think it's worth it. So.
Do you know anything about the progress with these frameworks that do their own WSGIs now, like Tornado or something like that?
As far as I know, nothing does support it, but it's not difficult to send link headers. So, I mean, sure. Yeah, it should be reasonable.
For those people leaving the room, if we can keep the noise level down, tiptoeing. Thank you.
Hey, maybe addressing the previous question, but in order to support server push, do you need H2 end-to-end?
I'm sorry, can you speak up?
In order to support server push, do you need H2 end-to-end? And are there any workarounds for that?
Yeah, so to support server push, you do need H2. It is a feature of the protocol. So yes, end-to-end needs to be H2. As far as like proxies and caches in between?
Yeah, like a Akamai DSA, going to H1 origin or something.
I'm actually unsure. whether they would see, because it kind of looks like a regular HTTP request, but it is H2 protocol. So it kind of depends how they handle stuff they don't know about at all. It's non-HTTP traffic, which is what it potentially may look like. And it may be that they don't support push directly, but they support H2, because there's varying levels of support. And they may do it accidentally. Like, I hate to use that word, but like that may be the case. So yeah, it's something to look into.
Thanks.
Hey, how much control does the client have over what gets pushed? In other words, can you send as part of the header, say, give me pushes, but no pushes that are images, and then how does that affect dependent pushes?
Right, so it's ultimately how much control. So first of all, the client is in 100% control of what it accepts, but not what is pushed. And as I mentioned, there's a push promise header, which contains like what it's trying to push and some information about it. And you respond with either a continue or a stop. And at that point, it's up to the client to decide how it's going to handle those responses. Now in curl, there's like a, it actually gets added to the multi-request. So even if you're doing a single request, you would do it as a multi-request, and pushes would just get added to that, and you would handle them. But it's the same sort of logic you were going to use as if you would make those requests yourself. So.
Thanks.
My question is much along that same line. Are they exposing the fact that you're getting pushes to in JavaScript at all, or is there any way to see this from, say, a JavaScript app?
So JavaScript plus push?
Yeah.
As far as I know, there's nothing yet. Sorry, I would love to see that though.
Yeah.
There probably is in Node, right? But that's not browser. So.
Do you see changes in how developer tools will grow to see what the changes or dependencies are, or how these are pulled in?
Do I see changes? I hope so. I hope that all of the build tools that we have, like Grunt and Gulp and all these kind of things that are currently building like all of our dependencies, asset pipelines, things like that, will start to get smarter about this concept of multiple H1, H2 stuff coming in. As far as like determining what dependencies are and what their priorities should be, I think that might be some sort of learning thing that's going to happen. We're going to observe traffic, especially when it comes to automated pushes. We want to see what users are requesting. Oh, when you request this, you also always request that. So now we're going to start pushing that. So I think we're hopefully going to see some of that stuff. But we're a long way, we're a short way into this journey. Is a long way to go still.
And are there, will there also be new tunable things?
Tunable?
For say large environments with servers with HTTP2, like where they would currently use keep alive close or keep alive.
Yeah, I mean, I don't want to speculate because I'm not the one making the decisions, but I hope that we're going to see a lot around this. So.
Thank you.
You mentioned that CSS and JavaScript minification don't matter so much with H2,
yes.
And I'm not quite sure why that wouldn't be an additional benefit. Could you explain that?
So the difference between just gzipping JavaScript and CSS and gzipping plus minification is about 1% generally in terms of file size. The benefits of pushing will make it more performant than saving the extra 1% because it's already in their cache. They don't have to make the request. They don't have to parse the HTML to see what they need before we start sending it to them. So there's kind of like a potential idle time there. They've received the content. They're still parsing it and laying it out and reflowing it or waiting for other resources. During that sort of holding time, that's when we're sending them the push stuff, or simultaneously actually as well if they've got enough bandwidth. So that would completely blow away that 1% cost savings. So, plus less resources on the server side as well. So. Right. Is that it? No more questions?
That's it. We're done. Let's all thank Davey again.
Thank you.